So we first did this for galaxy groups, so there's not too much study on galaxy group. So it's followed up by Laura Parker for her thesis, where you basically have a whole bunch of galaxy groups and you stack the signal together and you detect the lensing signal and measure their masses. But Sloan has done this at a much larger scale, and this, I thought it's nice to show the very nice work of Dave Johnston using the SDSS. So this basically, they bind the clusters in basically the luminosity within R200. And you see the lensing signal here. And so this is really nice. So Sloan is not very deep, but because of its enormous survey area, they get very low signal to noise per cluster, but they have so many clusters that they get a very high signal to noise measurement. And so here you see the clusters as a function of, well, luminosity or richness, and you can see the masses go up, and the signal has decomposed in various components. You can see the NFW profile, the central galaxy, and you see here they also try to account for the centroiding errors, although I think there's a little bit of discussion whether they overestimated that effect. And you can see here also the contribution from the clustering of clusters. So really this is amazing, like the signal to noise you can get in these measurements. And what you can do is then calibrate the mass richness relation, for instance. So you basically say, I'm going to do a cluster survey, I count the number of galaxies, but this calibration has told me what the mass of this cluster on average is. And look at the error bars, it's really quite remarkable. I think this one is particularly nice, done by Eli Rykov, because now both axes are stacked. So what they did is, well, in Sloan, well, there's overlap with the Rosat All Sky survey. Well, none of these clusters is detected by Rosat, or maybe a few are, but there are still photons coming from these clusters. So on occasion, a photon has arrived. So let's find these clusters in the optical, stack all the Rosat pointings, and stack the lensing signal and plot the two against each other. So basically both quantities are stacked, but you see a very nice relation between the X-ray luminosity and lensing mass. But I think here it's good to make the caveat of the danger of stacking, because you have to really be careful what you do, because what it turns out, the richness of a cluster is basically counting the galaxies in an aperture, and if I have a cluster that's elongated along the line of sight, its richness will go up, but so does its lensing mass. So lensing mass and richness are highly correlated, and so this is binned in richness. So you could say this is sort of binned in lensing mass, but my X-ray luminosity, if I take that cluster and turn it around, is not changing, even though the richness and mass are changing. So this galaxy, for a given X-ray luminosity, can end up in different bins. And it's indicated here, where we looked at couple of clusters from the 160 square degree survey. So X-ray selected individual clusters using the HST. And what you find, there are clusters. So this is richness as a function of luminosity. There are clusters, and this is a CL0024, which is well-known, rich, massive cluster, but has a very low X-ray luminosity. And so there are more of these clusters. And so you can see in the lensing mass, LX, they are also a little bit high. But when you look at mass richness, so lensing mass versus richness, they all line up very nicely. And so that's sort of shows the warning of if you have this intrinsic scatter and you have some correlation between the parameters, you have to be very careful when you stack the clusters, because you can actually bias your relation. So this is where individual clusters can really help to sort of in the interpretation of these stacking analyses. And so this is a nice example of one of the clusters in our sample. And so the study we're finishing up is the Canadian Cluster Comparison Project with Andy Madavi, Pat Henry, Chris Fieldfeld, and Reef Babul. And so we basically picked of the order of 50 X-ray luminous clusters of galaxies. We did more or less a temperature selection. And the aim is to study the ICM and also calibrate cluster abundance study. And recently we actually started a low redshift equivalent to also do this, but also study the properties of dark matter halo-zinc clusters, and actually do a study of type 1a supernova rate as well. Just jump to the results here. So this is our plot of the lensing mass as a function of X-ray temperature, and you can see there's a very nice relation here. So this is quite nice. So temperature actually turns out to be a very good indicator of the cluster mass. And so this is this is the first time we have such a large sample where we can look at this. And what is also interesting, what we have is measurements of the central entropy. It's essentially the temperature of the density to the power 2/3. And so what is interesting, so if you have what are the cool core systems, so the systems with people, so I'm not allowed to say relaxed because some of the high entropy systems are also potentially relaxed. But these are more or less the cool core systems, and actually those are also in the following plots indicated with open circles. And yeah, if you squint, you can see that the scatter for these clusters is much less. And also when we do the fit and we take into account the scatter, we find for most relations, this scatter is almost consistent with no intrinsic scatter. And remember, this is comparison with X-ray, so just the projection of the cluster, just the way it's oriented along the line of sight will introduce some scatter. So the scatter is assumed to be log normal. So that's quite interesting. Well, so one thing we can do is also compare to Sunyaev-Seldovich measurement, and that's indicated here. So these are some results from Bonamente, and we match to the same radius. And we find that actually the true SZ, so the thing you measure with an SZ survey, has quite a small scatter. So indeed, SZ is a very good indicator of mass. And again, lensing is critical to calibrate these relations, because SZ by itself isn't, you can sort of write down what the mass should be, but you're never quite sure. And so this is also what Tim mentioned yesterday. So for SPT, we got data or time on HSD to calibrate their relation. But you can also construct a similar relation from the X-ray data. It's basically the pressure, so it's basically the YX here is the gas mass times the temperature in the cluster. And in simulations, that is supposed to be very, very tight. But the observations don't, although it's quite tight relation, the observations don't quite support it. So this is where the lensing is quite important, because the lensing really provides a test of what you see in simulation, because what is typically lacking in the simulation is good prescriptions for feedback. So the AGN in the center of the cluster changes the thermodynamics of the intercluster medium. But again, you see here these white points with almost no scatter. It's quite remarkable. So something we did a few years back with Andy Medavi for a smaller sample is compare the lensing masses to the X-ray masses. So that's sort of the most obvious things you could do. And what we find there is that when we look at sort of small radii where the mean density is 2,500 times the critical density, we find there's very good agreement. Whereas if we go further out, so where the overdensity is smaller, so it's larger radii, we find that that ratio is about 0.8. And what this suggests, and it's in good agreement with what people have seen in simulations, is that the gas at large radii is not in hydrodynamic equilibrium. And again, so this is only with lensing that you can find this out, unless you would blindly believe the simulations. Right? Because the X-ray masses, they just seem to correlate with the temperature perfectly fine, but in reality, they're systematically biased. So we repeated this for a full sample, and because the sample is now much larger, so the previous work had 15 clusters as a whole, now we have 15 clusters with low entropy, and this is the full sample, and this was very striking. So you really see a difference between these low entropy systems and the high entropy systems. So they're clearly offset. This has no intrinsic scatter, they have quite a bit of intrinsic scatter. So that's also interesting. So it almost starts, a picture is emerging where entropy really allows you to distinguish between two classes of clusters. And I think this is a bit complicated for cluster abundance studies. So we really have to try to understand what is going on here. The other thing which is rather puzzling is this very high ratio of X-ray mass over lensing mass at R2500. And what we're worried about is that, so this is an analysis combining Chandra and XMM data, and this seems to be largely driven by Chandra data. And so the worry is that there's still an issue with the Chandra calibration, because this is actually very strange. Like, it's very hard physically to come up with mechanisms which would cause the X-ray mass to be higher than the lensing mass. And again, so this is actually quite nice, where lensing with these very large samples of clusters can already pinpoint potential issues with the X-ray calibration. So it's something we're looking into right now.